If the Earth is unique now, or if we can consider the Earth unique, it's just because we have an enhanced understanding of what Earth is in its properties, and more importantly, maybe all the processes that drove these properties now. And of course, in the ancient time, when we didn't have this knowledge, we could consider, or they could consider, that essentially the Earth is a body of a given mass, possibly a given distance to the star, the Sun, and so to find elsewhere a planet with similar properties, although of course we never get exactly the same mass, exactly the same distance, and so we know that just because of very tiny differences we'll not have exactly the same pattern afterwards, but it could be sufficiently similar for the people to consider that elsewhere there should be, or there could be, Earth-like planet. And that's still the case, actually, that some people consider that mass and distance are sufficient to describe a planet and its evolution. But actually we know that it's not the case. We know that the evolution of the Earth is not merely due to mass, distance, and so macroscopic parameters. Many other properties or many other factors intervene to fascinate, to really pave the evolution of this planet towards what we see here, the atmosphere, the water, and the clouds, and many more properties. So we know that if we want to have that planet, it's almost impossible, because we know that these are governed by the contingencies, and we have seen for the two examples that we have taken, migration on one side, giant collision on the others, that if a very tiny subtle parameter is changed, then immediately the subsequent evolution will be entirely different. So that's why we cannot qualify of exo-Earth something that would only have these macroscopic properties similar. And that's why really we cannot have now what the ancient people were forced to consider, that the Earth as equivalent anywhere else, knowing what Earth really is and what the processes were to drive the Earth up to where it is now. One of the examples I want to put the emphasis is on this question of habitability, has to do with the temperature of the surface. For water to be stable, you require a given temperature, that is clear. It's clear that most of the energy comes from the stars or from the sun, but the sun by itself does not govern the temperature sufficiently to say the water will be liquid and the ocean will be stable by themselves. We have seen the effect of the moon, for example, but another thing which is important, that even with the moon stabilizing the obliquity, the temperature of the surface of the Earth and governing the temperature of the ocean themselves is governed essentially by the greenhouse gases and CO2 in particular. And we know that the CO2, very tiny amount, a few hundreds of ppm that we have in the atmosphere, out of the hundreds of bars that we might have very early on, is entirely recycled by the activity of the Earth, and the activity of the Earth is governed itself by the radioactivity of uranium, thorium, and potassium in the mantle, in the crust, which has nothing to do with the sun. And without that greenhouse gases, which again is very tiny, we would not have the temperature that we have. So even the temperature and the stability of water as a liquid depends on essentially the composition of the atmosphere, which itself is driven not by the star, but by many other factors which are also contingent, in particular the radioactive content of the inner volumes of the bodies. So again, even the habitability, just considering the water be stable, could not be translated only by the mass and the distance to the sun. The time at which it was accreted, for example, will force, or essentially the content, the radioactive content of the interplanetary, or not only interplanetary, but interstellar medium in which the nebula will form and accreted, will be fundamental. What I wanted to say here, that the unicity of the Earth is really the result of all the contingencies that drove the evolution. But the next question now is, among the properties of the Earth, it harbors life. Is life also a result of this very specific evolution? In other words, could we be forced to consider that life is a property intimately coupled to the evolution of the Earth, or is it generic, sufficiently generic or generic enough to be also found somewhere else in the universe? So that's what we'll test now, And my starting point with that will be a few remarks concerning what we found with Rosetta and Philae, because really they modified a lot, even the concept of what we called life. So we have seen for the unicity of Earth, with two examples, migration and giant impact, how we can understand the course of diversity. Now we'll discuss the question of life emergence. Rosetta and Philae has really triggered an entirely new of what life emergence is, at least for me, and I would like to tell you what I think has been fundamental there. First of all, this image, which I'm very moved every time I see it, it's an image that we made from Philae itself after when we stopped finally our very big and traveled journeys. We finally stopped in an alcove where, although here you consider that there is some sun here, we have stretched dynamics, essentially it's essentially dark. There is no sun arriving there. That's the reason why we could not really reactivate the battery themselves and recharge the battery and reactivate the activity of Philae after a while. But during the first 60 hours, well, we could observe it. We confirmed something which is one of the major results, I think, of both Rosetta and Philae, that the bulk of the material is not ice. There was always this idea that a comet is essentially made of ice, and we had this idea just because when a comet comes close to the sun or to a star, it essentially, the ice sublimates and it makes this big tail that everyone knows as really the sketch of a comet with a coma, and that's why it's called comet, which is an envelope, and the tails. What has been shown here that the ice is only maybe 10, 15, 20%. All the rest are grains, and the majority of the grains are carbon-rich grains, organic grains. And that's why I made this acronym organize. If you put an E at the end, organics, as you know, means organic matter in English. If you put an E there, it's organize, meaning that the ice is really embedded in the organics. That's really what a comet looks like. So that's the first point. The second is that we have seen that instead of being an ice, it's organics, but it's very fluffy, the density is very small, and as you know, we essentially had rebounds. And the reason why we rebound is that this material, just upon compression, make like a trampoline effect. It condenses like a crust. And this crust actually is very important because the organics are embedded in something that could have this sintered crust protected such a body when entering the early Earth's atmosphere and preserving the organic material inside from being destroyed during the entry. And eventually this material could have been spread in the ocean there and really be seeded there like real seeds. So that's one also of the results that we had here. But most importantly, this organic material here, the grains which are here, are really grains which have been manufactured prior, of course, to the comet to be formed itself, as a result of all the evolution of the organic chemistry in space, from the interstellar medium up to the clouds in which they sort of accreted and condensed, and then during the collapse and the rotation of the disk, there has been also an evolution there, in particular because at the center of the disk, the sun finally formed, and when it formed, it irradiated some of this carbon-rich material, modifying the composition itself. So every specific evolution with the sun in particular irradiating at a given time might have changed the properties of the grains, and so I do not consider that the grains in this comet are similar to the grains in any other comet in the solar system and or the comets formed elsewhere in another environment. And so in our specific solar nebula, the irradiation of the sun, for example, might have modified the chirality of the grain themselves. We have demonstrated, a colleague of us, Louis Dandecourt in Orsay, has shown that when you irradiate it with a given radiation field, some grains, you may induce homochirality, very similar, mimic exactly the chirality we have in living organisms. So all that to say that as a sequence of result of the sequence of evolution of the carbon-rich material in space, from the way they are formed in a star environment up to they're embedded in a nebula, there is a lot of different reaction which be contingent to the very specific way the collapse happens. So that's part of the reason why we consider that the material there that we have started to analyze within Philae have already some specific properties which will be very helpful afterwards. And the afterwards is what? The afterward is that this material will finally impact the oceans of the Earth, because they will even form part of them, because they are bringing some water, as I said already. And then the next cometary nucleus will bring in this water these very specific grains. But again, what is important is that it's not that it's water, it's a very specific water. If you have clean water, the clean water, how we know, is not habitable. If you put a fish of an aquarium only with water, pure water, it will die immediately. You have to have a lot of ingredients there. You have to have a given temperature, a given pH, acidity. You have to have several cations, several catalyzers. Everything that will make this water very specific will force orient a given organic evolution. So all the continuum of processes, from the formation of organic grains as we see them in a comet up to the time where they will form living structures, go through steps of reactions which are contingently paving a very specific evolution. And this is absolutely, I think, fundamental in the process now, that we consider that the life as we see it on the Earth is the result of this continuum evolution through very specific reactions, patterns imposed by the context, what I call the contingencies. So there is, in the common way of looking at the origin of life, the idea that life together in the diversity of, everyone knows that there is a biodiversity, but they have something common. And what is common in life would be what they call the principle of life. Some specifics of life, like survival things or whatever it is. And that would be entirely, this principle will be excluded from what we call the inert matter, or what they call the inert matter. There is some inert matter, like a stone with respect to a tree, for example. There is a difference in nature between one and the other. Is considered, at least that is the basic consideration now of how the matter is divided into inert material and living material, with principle on one side, the not principle on the other one, and transition that will be emergence of the principle. So that's the way the people consider normally, and they are looking really at what are the principles of life, and what, for this principle of life, would drive their appearance or emergence. This is a very common way of thinking, and this is why I think there is other way, and this is what I propose here now, other way of thinking the evolution towards life here, because this strict emergence here is very uncomfortable, I think. And that's why I said that there is several issues with that concept now. What are the life principles? What are they? How do you define them? And it's very strange that when you discuss with 2 or 3 biologists, we'll have 4 answers. It's not trivial to define them, because essentially we are, and I will finish by that, I think, we are in an ideological concept that exists. We have, again, a stone and a tree are different in nature, and they will try to define what a tree is as a living species in that concept here. I think this is really a very difficult thing, because then it will go, as we'll see, toward the origin, and it's, of course, creationism would solve the issue, but you cannot validate that. If you want to have something that you can validate, you are blocked like against a wall with that. So what are the principles? Do they really exist? Can we really say that the principle that you will use to define life are really absent in what you call the inert things? And I will go back to that. How does the emergence of these proceeds? And if you don't believe in creationism, or if you want to avoid that. Number 3, how does the selection of ingredients operates? We know that in the DNA, in all the living organisms, you have only a very few numbers of molecules embedded there. You have only 20 nucleic acids, you have only 1 type of sugar with 5 carbon atoms. You had many more before that. Why didn't you use the others? What were the selection process of that? And that's a real question here. The 4th point here is, what are the prebiotic species? I don't like the idea of even quoting anything prebiotic, because if you say something is prebiotic, you mean that necessarily it will go towards life, right? There is nothing written there. There is no arrow. There is no direction in which things should go or will go. That was typically the debate between Lamarck and Darwin. Either an arrow saying, well, we have to go to higher complexity, we have to go to that direction rather than another one. Darwin has exactly demonstrated the opposite. At every step of the evolution, all what he called the varieties, all the possibilities exist, and only the context with select something, one preferred to another one, just because it's higher in efficiency with respect to the predation. So no, there should not be direction there. And so if there is no direction, you cannot call something prebiotic, because then that you would assume that this molecule will go to. That's number 4. And number 5, which I think is important, the famous mono question, hazard and determinism. How do you play with that? If does really life had respond to very specific principles with hazard contingencies that would be out of the laws of physics and chemistry, which are deterministic by nature, or is there a possibility to combine them? So I will rapidly touch all of them just based on our understanding of the origin of diversity for the solar system, to try to see if the diversity within the biology and towards life, even before life, towards what we call life, can be explained in the same direction. And so as you will see, what my approach, what I propose, is very distinct from this emergence, and I think it's sort of answer to all the issues that I have just brought here. First question, this question of the life principles. This question of life principles is again in the idea that you should try to explain why a rock and a tree are different, why there are some specific ways life operates. And one of the common thinking of the people normally is to say, well, it's autonomous. Life has a lot of autonomy, self-replicating, is autocatalysis and that sort of things. I think it's misleading to say so, because whatever structure or living structure you take, per definition, is not isolated. If it was isolated, it could not, of course, bring energy, bring ingredients. So this question of isolation is wrong at a given point. And all what has been said concerning the second principle of thermodynamics, saying, well, everything has to go from order to disorder, and life goes exactly the opposite way around, goes with that idea that life is different from physics because it does not respond to the second principle. But that's not true. It's just because the second principle applies from isolated system, and life is not an isolated system. Without the sun, without the possibility for even to the molecule to extract energy from the environment, you would not have life. I mean, what we call the death is per definition the stopping of this input of ingredients and energy from the outside. So even the autonomy principles, like self-something, self-replicating, whatever, is, I think, biased. And reproduction itself. We said, yes, a living organism per definition reproduces. But there is a lot of systems that you would call inert that also reproduce themselves. A dynamical cloud, for example, it will shift in different subsystems that all of them will also try to reproduce. For example, now everyone agrees with the sentence like poussière d'étoile, we are stardust. Why that? Because it has been understood that all the elements that constitute the bodies and everything goes from stars somewhere. So we have an history, and that's fundamental. Our history is the universe history, because we had to have the 15 billion years or the 13 billion years of evolution to get to what we are formed out. But the problem with that is that the people do not realize that the star dust only refers to the past. That after our past, there is a death, and then we continue to recycle things. So all the evolution in disks, in dynamical evolution, the chemical evolution of the universe, whatever, goes from the same sort of thing, that we also reproduce things, and we have the same sort of mistakes in the reproduction chain, and because of the mistakes, things go in that direction rather than another one. That's why the planets are different, because we have the same elements at the beginning, but when you do the crystallization, it depends on the environment here or there. When you say, we spoke of the clouds, the way the clouds form also depend absolutely intensively, profoundly, to the nucleation sites and to the environment in which they are. So you have, for a lot of inert systems, when you grow silicon, for example, the interaction between what you grow and the place in which they grow will make the differences, and that's really the real problem, actually, of all the silicon systems. So there is a lot of things that goes with, and you could really have bouncing and bridges between the two. There is a few things which are not equivalent, and what is not equivalent is time constant. The time constant for evolution is so long for most of the inner system that during our life we have no way to materialize it. And so a stone looks the same when we are born and when we die, we think. But it's not true that it's forever. If you look at longest time scales, of course you can see things. And actually even living organisms, the evolution of species are among millions of years. You need millions of years to have the evolution of the chains. Human, for example, the evolution of mammifers also went through a lot of different modifications as a function of time by over thousands up to millions of years. So this also we don't see. But we know through the fantastic Darwin theory that the long-term evolution is really made of very short-term ones. And with the pandemic, we know that for the various time scale of a few days, you have mutation that goes to other species. So it's true that we have taken our own experience of the time constant of the evolution of living organisms because we see them, we hear our heart, we have a way to understand the short time scale of evolution of living objects. While we don't see that for a tree, for flowers, for everything, we see every spring that things are renewed, whatever. But we consider that by contrast, the inert matter does not evolve, and so we consider, some people consider that even evolution is only on one side, the living species, and not the other. I think it's not true. I think that both evolution and even what they call reproduction, the time is not good because you never copy exactly the thing, so you copy with mistakes. This is also something that happens in the inert system. So all that to say that even this question of life principles are not necessarily really exclusive to life, and I think that the same products can be explained for inert matter. The next question was this question of the emergence, and that's more of even a philosophical questions. We love to have defined states, classifications. We hate to see the transition between them. That's in the social context, you know what I have in mind, but that's true for everything. We like to see a tiger is different from an elephant, so we consider there are tiger and elephant. We do not accept this idea that there is a continuum of evolution over the time and space, and the same applies from inert, I think, and living organism. But the fact that we never like to see the transition prevent us to see the continuum of processes of transition in a given evolution. To me, there is not a single step out of which you can say, after this step we have life, before this step it's inert. I think we have a continuum of evolution from the carbon chemistry in space up to what happened in the comets, and then when it goes to the oceans, and up to now. And so the evolution of organic chemistry is over billions of years, and then of course in some cases it goes faster, but there is really a continuum. And to me this question of the origin tells me or reminds me what we said about the origin of human beings. At some point, because the Bible said so, we had a day where you had the humans and the day before you didn't have. Thanks to Darwin, of course, now we know that's not the case. It's not a rapid, it's a slow evolution with a lot of here and there, defined essentially by the context, that finally end up with something that. So even the notion of origin for the man or human beings has no sense really. And to me, the same for life. Origin of life in terms of a really given emergence at a given point in date and space, saying, well, we go from one state to the next, reflects our way of thinking, which is, and when I say our, it's very specific to what we call the Occidental view of, for many, many principles with phenomenon and whatever. In China, in most of the Asian philosophy, you will not have that, because the focus will be not on the states, but on the transition between states. And when you do that, immediately you have a continuum, and if you have a continuum, you do not need to classify and to say that's life, that's not life. So that's how I would say that this has to cope with the evolution of life, and again with the diversity of possibility at each steps. So this question now of the selection of the ingredients, it's a key question. You have hundreds of amino acids detected, and in some meteorites, as you know, there are much more amino acids than the one that finally will be used. You have a lot of bases that you could use. You use only 4 in the thing. Why that? You have to have a selection process. This selection process, to me, is not a magic one. It's something which is based on a very high specificity of the grains which were there, and the specificity of the water and the reactions with that catalyzer which were present at that time. If you were in a different environment, different temperature, different pH, different irradiation by the sun of these grains rather than that, you will have other properties. These other properties will make or induce other type of reactions, and finally other type of structures. But these structures have no way and no reason to be quoted living species, because they will not operate with the same concept that we have with the Darwin theory. So again, I think that this selection of ingredients is fundamental, and I think it's entirely determined by the very specific properties of the grains, the water and whatever, in which the evolution takes place. And again, exactly as we saw that for migration and the giant impact, if something changed in terms of the composition of this and that, the ratio cation this rather than that, you will of course have something else. It's not that we'll have nothing, the carbon chemistry will not stop, but it will give something entirely different with no reason, because again there is no principle of life to call that as living organism. Then this question of enabling probiotic, I think I have covered that already, so we don't need really to elaborate more than that. Contingent, again, has manufactured what was required to get to the evolution that we contemplate on the Earth, but it's not because we contemplate that on the Earth that it is universal. So now a question of hazard and determinism, which is really sort of key, because normally it's said that in physics, whatever, the laws are deterministic, which is true, but why do we have hazard, and why we have hazard for life and not in physics? And I think the answer is sort of straightforward. We have also hazard in physics, but it does only translate something very special, which is the fact that we are not capable of identifying all the processes involved in something. When we say, for example, that, I don't know, a given meteorite arrived exactly here. If it arrived somewhere else, it would have done something entirely different. But we could not know whether it come here rather than that, so we say it's just a random. It went here, it makes this. If it went here, it would have done something else. It's only because we do not have all the information that would allow us to know that this body left another body and then crossed the interplanetary space in that way, and the Earth was here or there. If we had everything in our hands, we could, of course, know exactly the trajectory and understand why it went here rather than there. No one would have conducted here, but we could retrace and follow the movement entirely. So everything is deterministic from that point of view in nature. It's just our incapability of understanding all the parameters that we say, okay, as seen from us, it's just random. That's one thing of the difference between the determinism and hazard. But there is also something different, is that we know now from the chaotic theory of Poincaré, which was in 1902, so really it's long before, that if you really want to know exactly, for example, a trajectory, the force is important, but not only that, we have to know the initial conditions of the movement. We know that if there is a small change or a small difference in the initial conditions of two things, after a given while, the trajectory will be sort of chaotic. Doesn't mean that you will not know where to go, but you cannot predict it to the level that might be necessary to predict something. Meteorology is obviously something that everyone knows, but for example, you play tennis, you want to send the ball in that place. You know that if you give a huge force here, it will get there. If you want to redo exactly the same afterwards, you will be incapable of doing that. You will try to, but it's never 2 times exactly the same. The same with the football, of course. You take, I don't know, a flower, a rose. Every spring you will have new rose. When you look at the rose, or different roses in the same bush, you will see that there are not 2 strictly identical. They are all different. It depends what your distance from the rose to see. They are all different, but still they are sufficiently similar that you know it's a rose. So that's really the key things here. And then you can really understand the difference between the coupling between the determinism and the hazard. There are differences. The question is, what is the level of differences with respect to what will determine the evolution? And as a rule, the contingency will play a larger role if the energy involved in the evolution is lower. When you have huge energies involved, like what you call the strong interaction, which only operates in stars, you know that when you have hydrogen with huge energy, because it's very hot, millions of degrees, it only can synthesize helium. The number of possibilities is very limited. So if you know the starting point, because the energy involved is so high, you know essentially how to predict the rest. It's almost entirely deterministic. And that's why we can classify the stars. But as soon as the level of energy is smaller, down to what is included in the chemical evolution and even the different chemical forms of links, then it's so small that you can really rapidly intervene with something which would have seemed to be not influential. When I say for the tennis, for example, if the wind exists, but if you have a huge velocity at the beginning, you have to have a huge wind to get the ball back to you, right? If you only send it very slightly like that, of course, the wind might be efficient here. So it's exactly the same in reactions. And the fact that for living organism, it's only what we call the electromagnetic energy which is involved there, the forces, interaction, with very low level, less than 1 electron volt, then any sort of factor that will have about the same effect, because the temperature might be important then, and by the temperature you add a new energy there, you can modify the determinism of the initial force to something that finally will cause a huge variety of possibilities, and that will cause the diversity of the evolution there. So again, it's not that someone else here will randomly impose something, it's just that you cannot control all the factors, and you will less and less be capable of controlling the factors if the forcing dominant force is at very low energy level. And with that in mind, you can sort of compare what happened with the inert and living organism, and you will see that there are a lot of bridges between the two. So the ancient paradigms were the one that we discussed previously, right? With essentially complexity increasing, and you know how to put there. There are a lot of things in that which were conceived as fundamental, which are fundamentally, I think, wrong. And one of them, of course, is the arrow. The fact that you have an arrow, you know where to go. It means that, of course, different things. It means either that someone wanted to, that someone controlled the evolution, and you are forced to get there. And even if at some place some contingent things arrive, you still have the idea that you have to go in one direction. And I think that although it's still the dominant way of thinking in our world, I think that there is a lot of reason now to consider that that's not the way it goes. So what I like is to build another sort of diagram in which you don't have any arrows. I put that still in the same order for the people to sort of balance it with the previous one. But from the Big Bang itself, you go to atoms, but you are not even forced to go to these atoms. There was nothing written in the marble that with 3 quarks you have to combine them to make 1 proton. You could have think of an either contextual environment in which other sort of particles could be there. And then from atom to molecule the same. You could really think of other content that will make something different. And so if you want to go from the Big Bang to life, which is put here, I feel that, sorry, it's in French, I did not modify that, but you can understand that V is life. It's not a single line, it's a and there are much more than these, of course, here. And what is important that life goes only in one of the branch. Many of the other branches goes with a lot of evolution. You have a lot of organic matter here and there, but what we call life is only on one very specific one. What I could not put here, because it would have made the diagram too complex, is to put the solar system on that. And this is, of course, on what I would like sort of end here, to summarize what I think, as I say here, very highly controversial conclusion. What I think is that life is really the result of a very complex suite of reactions, each of them dominated by the contingencies, again, by the possibilities to have a lot of different branches, and only the context will favor that. And what I call the context is the mass ratio of Saturn and Jupiter, or the mass ratio of Theia with Gaia, or that sort of thing, the angle of impact, or whatever you want. So there is a lot of, the diversity is probably more than infinite. If you look at the migration, for example, for Saturn to start its migration at a given state requires a lot of different parameters fixed, but they are not been frozen forever. They just are themselves the result of the previous evolution of the cloud. So again, life is only one specific evolution to me of the organic carbon chemistry. And if I put that, it's just to say that, of course, carbon, for basic reasons, has a lot of capability to make compounds, molecules. You cannot avoid, when you put carbon somewhere, that if you have an oxygen or whatever goes there, they will go together. That's the result of the electrical property of this atom. So carbon chemistry, of course, exists and will exist and has existed and it will exist in many different fashions, here or there. But the very specific way you will construct the carbon grain, for example, the carbon polymer or the carbon complex chemistry, will be the result of a rather complex mixtures of contextual constraints that will, in one case, very specifically, lead to what we call life on Earth. So you understand where I want to go there, that to me, even exobiology, although it's an exobiology course here, it's probably a biased and misleading word, because I really consider that life is intimately connected to the idea, to the evolution of the Earth, because if the Earth had a different evolution, the water would have been different. The evolution of the continent water, for example, putting the cation there would have been different. The tectonic recycling of species would have been different. And so it's not to say that you would not have had anything, but you would not have what we call life. So that's really the first point here. And so there, clearly, to me, life is intimately coupled to the evolution of the Earth. So I said afterwards, this is really only possible if we understand that the diversity is key to all evolution. So there is no arrow, there is no grid need from anyone to control that. So that's against many of our ideological direction of thinking that we had over the centuries, acquired, and then we are still here. So that important. For life to be understood unique, I think comes from the same process that happened for the Earth to be understood unique. The Earth is unique only now because we understand the properties of the Earth in a much more detailed, refined way that we did in the past. Copernicus had no way to understand that the Earth is different from the other planet, because for him it was a body at a given time, at a given mass, rotating around the sun at a given distance. With that in mind, of course, you may have that exactly at the same, because you don't have the chaos in his mind, you may have that repeated as many times as you want. And for Giordano Bruno, of course, it was the same, because they had no possibility to invest themselves in the properties of what the Earth is. Although he saw the diversity here, he had no way to know whether or not such a diversity is unique. Now that we do know that, and we do understand the reason why, I think we understand the unicity of the Earth because of that. And that's why I think that what we have said already today, the search for exo-Earth somewhere else is, to me, something like a nonsense or an ancient view, I would say. But for life, I think we are very close to that also, but with some delay. We are not at the same stage to understand all the processes that paved the evolution of the carbon organic matter from the initial cloud up to now. So we don't know precisely what the composition is. We have tried or started that with Rodella and Philae. We are now completing that now with samples brought back from carbon-rich material back to our lab, and with the mission Hayabusa 2, we are exactly in that configuration. Then now we are in our labs the carbon-rich material to be analyzed, and we'll try to see if it's possible, with the few grams of material that we have, to understand the specificity of these, for example, with respect to criticality, but also for others that will explain why out of these grains, put in a very given and specific environment, water with this rather than that, we can go to the complexity of the biodiversity we see on the Earth. But again, it's very important to understand that that is directly connected to a refined understanding of all the steps that paved the evolution of life. So, to finish with, lots of people say, yes, of course, we have life here, but we could have life elsewhere, eventually, in different forms. Saying, well, instead of carbon, you take silicon, instead of water, you take another liquid or whatever. That's not inconceivable, that somewhere else you will have another evolution. My point is that this will not be life. This will be organic evolution, life being a specific one. So I am against this idea that if you put, for example, silicon together, we know how to grow silicon. And it's true that with silicon you can have a lot of different structure, much less complex, because silicon is less capable of doing this polymerization that carbon does. But still, you have defects, you have point defects, you have dislocation, you have a lot of things that mimic the defects also in the carbon-rich replication organisms. But all the chains that left to this specific evolution that we call life is different. So I hate the idea to say, well, okay, what you say is fine, it's contingent, but somewhere else with other ingredients you will have exactly, finally, the same principle. Life principle, I think, do not exist. That's one key thing here. And when you continue in that discussion, and I will really finish by that, I think you go to this idea that during centuries and during decades recently, in particular with Darwin theory, the concept of life has been very, very powerful. And it was on an operational basis fundamental in enabling, in particular, Darwin to explain how life, within life, you could have this evolution in the diversity of what we see here with millions of species and this and that. That's really unique. But it's, at the same time, I think that what has enabled this theory to come now reaches a real wall when getting to the origin of that. We have discussed that today. The question of the origin by emergence from inert world, I think, reaches difficulty to be explained, and probably that translates the fact that this concept of inert and life might not be adequate or pertinent anymore now. In physics, we had in the past such concepts which were very, very useful, in particular the concept of force. When Newton says it's the same force that allowed the apple to fall and the moon to turn around the Earth, and to put a gravitational law, universal law there, to explain that, it's absolutely amazing. But then came, and the same with the electromagnetic things, with the electrons around the protons, the electrons turned around the protons. Up to the time when the people say that it's black magic here. How does the electron know that there is a protons? How does the Earth knows, or the apple know that the Earth is there? There should be some information that goes here and there. And so the concept of force itself has been forced to move recently toward what we call interaction, saying, well, if an electrons and a protons interact and keep one around the others, it essentially becomes constantly another force, another particle that we call the boson, just make this information goes from one to the next. You cannot explain. For gravity it's different because Einstein explained how the mass changed the local gravity, the local space actually. But for the three other interactions, the nuclear force, the weak interaction and the electromagnetic interaction, we know that some particles, the bosons, have been forced to be not invented but proposed before being discovered, and they have been discovered. And so that's why now the concept of force, which are so useful during centuries really, enabling, for example, to determine a trajectory of a body, that's fantastic. But beyond that capability, they were forced now to be overtaken, bypassed in a sense, and moved, changed to another concept that would really fit with the past and the future, what we know now. And I think that for life, we are very close to that now. If we are close by the fact that we don't need it anymore. It has been very useful to understand why within the biology on the Earth we can explain the evolution through the theory which has been built based on this existence of nature, difference of nature between a stone and a tree, as I said. But now, if you want to understand the reason why life was originated somewhere, has come to life, what is the process by which you have ended up with all what we see on Earth now, you are forced to go over what has been proposed as a discrepancy between two different distinct modes, inert and living organism. And if we agree on that, then the question of exobiology might be modified in its semantic, at least, translation. That's why I think life is very close to the point reached to make these changes. One step further should be made now. Okay, so that was the idea that we have now out of the exploration of the solar system. Just to finish, we started today with these charts saying, well, up to the space era, Earth was the sole planet, and we tried to extrapolate what we knew out of our understanding of what the Earth is, and the same for the solar system. We use the unification dogma to say Earth is a generic standard planet, life is a generic evolutionary process. I put some question marks, and after these 3 hours and after the space exploration, I think we can really stand that Earth is unique by the understanding of what Earth is. And I think really that it's more controversial, as I said, that life also is unique, being intimately connected to the unicity of the Earth.